Hi guys, Dr. B here. This is topic 3.6 and 3.7. Topic 3.6 is the deviation from the ideal gas law. The objective is to be able to explain the relationship among non-ideal behaviors of gases, interparticle forces, and or volumes. So gases behave ideally under ordinary conditions, high temperatures and low pressure. Kinetic molecular theory assumes that under these conditions the volumes of the gas themselves are insignificant and that gases do not experience any intermolecular attractions. This is assumed because under high temperatures they are moving quickly and fast enough, and they're under low pressure that they are distant from each other so that the gas particles cannot experience as forces of attraction to one another. However, all real gases do not behave ideally when at high pressures and at low temperatures. As pressure is increased, the particles are pushed closer together, which results in the volume of the gas molecules being more significant. As the temperature decreases, the particles are moving slower, and therefore they have more significant intermolecular attractions between them. Volume adjustment for gases under high pressure. The volume term in the ideal gas law equation is the volume of the container. It assumes that the volume of the particles within the container is negligible. That is to say that the volume of the particles take up the container is so small that it can be ignored. The ideal gas law assumes that molecules have no volume of their own and they can be thought of as point masses, since the molecules are so small compared to the empty space that it's considered insignificant. At low pressures, the actual volume of the molecules are so small compared to the high volume of the container, and it can be ignored and does not need to be subtracted from the total volume. At high pressures, the molecules occupy a significant part of the volume of the container, resulting in significantly decreased space which the molecules can move. Therefore, the individual molecules are now significant and adjustment must be made to the ideal gas law to calculate the volume. The volumes of the molecules must be subtracted from the total volume of the container. If a gas is under high pressure and low temperatures, if the volume of a container is decreased, this causes the pressure to increase, which also forces gas molecules to be much closer together. When the particles are closer together, their intermolecular forces become significant. In both the ideal gas law and kinetic molecular theory, we assume that there is no IMFs between the particles. However, at high pressures or low temperatures, this is not true. By decreasing the distance between the particles or decreasing their kinetic energy, the IMFs are no longer able to be ignored. Since the particles are closer together, they can now start to feel attractive forces to one another. Pressure is a measure of particle collisions to the walls of the container. If the particles are now feeling attractive forces, they tend to clump together more and will collide with the walls of the container less, thereby decreasing the pressure of the gas. Topic 3.7, solutions and mixtures. These are together because they're a relatively short lecture, for the 3.6 at least. The objective is to be able to calculate the number of solute particles, volume, or molarity of solution. So you should know molarity, which is the number of moles per liter of solution. Solutions come in the form of solids, liquids, and gases whose macroscopic properties do not vary due to the fact that the composition is uniform throughout. You can say it's a homogeneous mixture. For liquid solutions, the solute may be a gas, liquid, or solid. While there may be many different methods for describing solution concentration, molarity is the most common one that we're going to use, and that's used in the laboratory. So remember, molarity, capital M, is the moles, N, of the solute divided by the liters of solution. Properties of liquid solutions. The components cannot be separated using filtering. There are no components large enough to scatter visible light. The components can be separated using processes that are the results of intermolecular attractions between and among the components, such as distillation and chromatography. We'll talk about that later. Ion concentration. Ionic compounds associate into ions when they form solutions. Because of this, the concentration of the ions found in a solution of a given concentration may not be the same as the original solution. For example, while 1 mole of sodium chloride NaCl will dissolve to form 1 mole of sodium ions and chloride ions, 1 mole of calcium chloride will dissolve in water to form 1 mole of calcium ions and 2 moles of chloride ions, Cl1-. Because of this, a 1 molar solution will contain 1 mole of calcium ions but 2 moles of chloride ions. Therefore, the chloride ions will have twice the molarity of the solution. So how do we draw this out? So we have a particle diagram that looks a little cumbersome. So what I sometimes do when I'm doing this, I will say, where is it? Does it work? Cool. I will say that this triangle equals H2O like that. So it makes it simple. So we notice that we have CaCl2, but based on this, we have 1 CaCl2, 2 CaCl2. So we have 2 moles of this. So to illustrate that we have 2 moles, we need to put 2 moles of NaCl. So we have an Na plus. So similar Cl1 minus, shade that in. Na plus, Cl1 minus, shade that in. So whenever you're drawing this out, let's see, can we figure out how many water molecules we have? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. That's too many water molecules. So hypothetically, let's say that on the right side of the CaCl2, we had 12 water molecules, which we really don't, but let's just say that for the sake of drawing this stuff out. On the sodium chloride side, I want you to put, it should mirror the same amount. So we're going to have 12 water molecules surrounding these Na plus and Cl1 minus ions. However, you have to make sure that it's oriented correctly. So if our sodium ion is positive, the electronegative oxygen will be associating with that. So it'll be something like this. One, two, three, 4, 5, 6, 7, 8, 9, 10, 11, 12, something like that. Where you have to set a key and also you have to make sure that the number is equal on both sides. Calculate the volume of 1.25 molar lithium chloride solution that can be made with 13.3 grams of lithium chloride. I'm walking away because I need to grab my calculator, sorry. So, list your knowns and unknowns. So your volume in liters is your unknown. Your molarity is 1.25 capital M. You have a mass of 13.3 grams of lithium chloride. So you need to convert your grams of lithium chloride to moles of lithium chloride. So 6.94 plus 35.45, so 42.39 grams of LiCl. Grams cancel out. If I just, we're trying to find volume. So remember that when you see capital M like this is actually 1.25 moles per 1 liter for my molarity. So I can treat this as a conversion factor. So 1.25 moles of LiCl on the bottom, 1 liter on the top, 13.3 times 13.3. Denominator 42.39 times 1.25. So divide the two. I end up with 0.251 liters lithium chloride. What would be the concentration of chloride ion in a solution that was made by dissolving 10 grams of zinc chloride in a solution that has a final volume of 500 milliliters? So just so we're clear, the chloride ion, it is the moles of chloride ion for the concentration, moles of Cl1 minus divided by the liters of solution. Since zinc chloride dissociates into Z2 plus 2Cl1 minus, we know that there are 2 moles of chloride for every zinc chloride. So to find out the moles of solute, we need the moles of the zinc chloride. So 10.0 grams of ZnCl2, convert this over to moles. So about 136.3 grams. This will give me about 0.0734 moles of ZnCl2. I'm going to convert this over from 1 mole of ZnCl2 to 2 moles of Cl1 minus. That'll be about 0.147 moles of Cl1 minus. Now I'm going to divide that to get the molarity of the chloride ion, or the concentration of the chloride ion. It's going to be the moles Cl1 minus divided by the total volume. That'll give us about 0.294 molar chloride ion. All right, gentlemen, that's it for now. Let me know if you have any questions. Thanks.